that they want us to estimate the derivative of y, keeping in mind that this function y, we don't have an equation for it, so to find the derivative we can't find an equation and then take the derivative of it because there is no equation. So bottom line is we want to estimate the derivative, we're going to estimate it by finding a slope. So if we want y of 18, they just use the 15 and the 20 points and just calculate the slope. So 257 minus 292 over 20 minus 15. And if you calculate that correctly, it should be -7. And units here would be, we're subtracting a degrees Fahrenheit on the top. Time on the bottom is in minutes. So that would be the rate would be degrees Fahrenheit per minute. And the ultimate answer here was -7. And ultimately, again, what does that tell us? That at time 18, okay, the rate of change of the pi is -7 degrees Fahrenheit per minute. So again, if you have a tabular situation like this and they ask you to find the derivative of the tabular data, then you just pick the ones where the 18 is surrounded by, essentially. You got 15 and 20 are your two candidates. That would give you an estimate for the slope at 18. Other questions on that part?
Wait,
Anything else on this part?
oh, sorry, I thought you were going to ask me your
All right. On part D, it says use the model given in part C, which is our W equation here, to find the time at which the temperature of the pi is 300 degrees. So ultimately, they gave us a model for the temperature of the pi here, which is this. And ultimately, they in part C, we found the derivative of that and evaluated it at 18. Compare that to our answer we had in number 7, or no, part A, I should say. And ultimately, like in this case, they want to use the model to find the time when the temperature is 300 degrees. And again, the W is just the temperature, so if we put in our 300 for our W value, which our W, keeping in mind, is our temperature, then wouldn't this be our sentence we're trying to solve?
Oh, not the derivative.
No, they just want the temperature. When is the temperature 300? This is a temperature equation. W represents temperature. So we just either solve this. If it was on the non-calculator part, it probably wouldn't be because of the. It'd be pretty tough to come up with an answer for that without a calculator. But you can come up with an answer that doesn't look like -7, if you will, or whatever the case may be. Actually, it's a temperature, so I guess we're looking for a time. So. Should be somewhere between 10 and 15 minutes. But bottom line here is this is likely beyond the calculator part, which means you could just either solve it with algebra or you could put both of those into your calculator and find the intersection between those two. So if it's a calculator problem, you don't want to waste a bunch of time doing algebra. So just put it in the calculator and use your intersection command. But ultimately that's what we're trying to solve, is that one. What else? Number 1.
So in C, they usually tell you to find the value of the derivative of 18, but they give you the original function. So you wouldn't put that in the original function, 18, right? For T?
No, you put it in the derivative.
Yes, you solve that.
So ultimately, again, if it was a non-calculator problem, you'd have to find the derivative of this by hand and then put the 18 in it. If it's a calculator problem, though, don't you have a derivative command at a point?
We do?
Ender.
Oh, yeah.
So, like I said, if it's a calculator problem, would you even waste any time trying to find the derivative of this? If you do, you're doing just that. You're wasting time. Right? So just recognize that all it is a derivative at a point problem, and set it on the calculator part. Just type it in. Anything else on number 1? 2? Part B says use the data in the table to approximate the average population of the sugar mill over the time frame 0 to 10 using left-Riemann sums, pi of equal subintervals, show the computation. So keep in mind that this is a population function that we're given. Right? So if we want to find the average population, we're actually looking for an average value. You got to recognize immediately as soon as you read that that's an average value problem, which means our answer is 1/10, 0 to 10 of our y of t dt.
So the 1/10 is from the fact that
1/10 is that we're looking for the average value. Average value of any function is 1 over b minus a times the integral from a to b of the function dt, dx, whatever the independent variable is. Okay? So keep in mind that we need to make sure that we understand that it's an average value problem. If you recognize that, then that makes the job much easier, obviously. Now we know how to proceed. Okay, so we need to find, pretty much a giveaway, we got to find an area since they told us to use the left Riemann sum here. True? Subintervals here go from 0 to 2. They are uniform subintervals. So that means that each of our rectangles is going to have length 2. So we're going from 0 to 2, 2 to 4, and so on. And so our heights, remember, if we're doing left Riemann sum, we're going to use the height at the left endpoint, 2500, 2912, 3360, 3815, and 4330. You want to grab that, please. And ultimately, if we add those up, we're not going to use the right endpoint because we have our left Riemann sum.
Excuse the interruption. I need to see Cody next.
Oh, you just had it. Irony. Alright, so again, in the left Riemann sum, we don't use the right endpoint, so that 4875 would not be a factor here. Just going to add those together and multiply by 2. And remember, is this the final answer right here?
Missing them.
No, this is the accumulation, but we need to multiply it by what?
1/10.
By 1/10. So whatever we get here, this part right here is this, and then whatever we get from there, we're going to multiply by 1/10, and we'll get our final answer, which turns out to be
Multiplied by 1/10.
3383.4, which, again, we're looking for an average population here, and if you're looking at the populations they're given, does 3384 make common sense here to be an average of the populations?
Yeah.
If you'd have just added this up and didn't multiply by 1/10, would 33,000 and some make sense here for an average population? Questions on part B?
Would be people per year.
Not people per year.
People.
Remember, this part would be people times years, right? And then the 10th would be divided by, 10th is an amount of years again. So it would be people years divided by years, which ultimately gets us back to people. Good question. What else on number 2?
Can you show how to use the ender function? I don't even know if I know how to use that. Whoa, what did you read?
Math, 8,
Yeah.
and whatever function, just say it's 2x, comma x, comma 5. That would give us the derivative of 2x at x equals 5. Shouldn't be surprising since 2x's derivative is just 2, no matter where we're at.
Okay. I just did that.
So, function, independent variable, point in question. Alright, what else, number 2? On A, what would we use if we want 7 when we use just the 6 and 8 and do the slope again? So,
So y is of 8 minus y is 6.
so we're looking for y prime here. We have y, this is our y function. Wouldn't it just be this minus this over 8 minus 6? And again, we're dividing people on top, years on the bottom, so we ultimately get some rate. We get people per year again. See, they give us a model here for the population of a different town here. And they tell us that P is measured in people. Use the model to find the value of P prime at 7. So ultimately, wouldn't that be a derivative at a point problem again? So if we go back and use our ender command again. Our function is 2x plus 50 squared. And we want that at at 7 times 7. So we get 256. And ultimately, if we do ender, keep in mind if this was a non-calculator problem, this is a pretty easy function to find the derivative of, so you could find the derivative and plug in 7. But bottom line here is we get 256. And what would be the units on that if it was the derivative of this p function, keeping in mind that p is the population versus time. If I were to draw a picture of this population versus time and I found the slope of it, again, it's still a slope, so if I have still an amount of people in the y direction, still amount of years in the x direction, so it'd still be people over years if we did the slope, so therefore it'd be 256 people per year.
Will they screw us on the AP exam like that? Like have the same answer but have the like rate different or whatever, you know, have people, you know, like answer A would be 256 people, and then answer B would be 256 people per year.
Could be.
And we do that.
Is that the same numerical answer you mean?
No, like you said, you gotta find out what it's like 256 what, right?
Right. Yeah, I mean, the numerical part is whatever it is. I mean, ultimately, you still gotta recognize that it's the slope of this population function. So like I said here, if we're gonna calculate the slope of a population versus time, it's people here versus years here. And the slope is gonna be people on top divided by years on bottom if you're gonna find the slope. It's always gonna be y over x.
Yeah.
What else? So looking at that, what is this?
Average.
It's the average value of that p function, isn't it?
Just plug it in your calculator.
As long as it's on the calculator part.
Yeah.
Yep. Obviously, if it's not on the calculator part, you'd have to anti-differentiate. But you could either use substitution here, or you could multiply that out and just use your power function. Either way. But more important part is explain the meaning of this integral. This is the average population over the 10-year period. Or fine growth. What else on number 2? Alright. Number 3. On the function that we're given here, we have a temperature function again. Got a bowl of soup placed on the counter. Time is in minutes. Temperature is in degrees Fahrenheit. And in part C here, should look pretty familiar. We just had one just like that, right? Isn't that the average temperature? So it's the average temperature of the soup over the 12-minute period, measured in degrees Fahrenheit. And to find the value here, we got, if we want to find the value of that, we can use our trapezoidal rule here. What do you notice about the interval up there, though, if I go 0, 4, 7, and 12? It's not uniform, so therefore we can't use our normal h over 2 method. So what do we do instead? Just draw the trapezoids. We got 0, 108, and again, it doesn't have to be any kind of perfect drawing. We got 101 here, we got 799, we got 1295. Ultimately, if we were to draw those trapezoids as such, anytime we have a non-uniform subinterval, okay, just take each one, just take the 4 points in question and connect the dots, and you're going to make 3 trapezoids out of that when you have 4 points. And ultimately, if we calculate the areas of each of those, you know, the trapezoid area formula is as such. And so for the first one, the height here goes from the height, of course, being the x distance between these. Got 0 to 4 is the first one. The 2 bases are going to be the 2 heights given in the table up there, 108 and 101. So that's one of our trapezoids. The next one goes from 4 to 7, so that's a height of 3. The 2 bases are 101 and 99. And then the last one goes from 7 to 12, so that's 5. And the heights are 99 and 95. And then ultimately what we're going to do with all those 3 things? Just add them up. So plus and plus and equals. And according to my paper, it should be, if you add those all up, should be 751. Now keep in mind though that this would be the total, right? But we want the average, so that's why we still have the 1/12 out in front. So final answer then, if we do that, would be actually nope, I looked at the wrong one. Not 751. I don't know where that came from. Yeah, they don't even have the total here. Ultimately, that times whatever that is 100.25 degrees Fahrenheit, which ultimately would be the average temperature of the soup over that 12-minute period. I don't know where that other number came from, a different problem altogether. Alright. What else on that one? Anything else on number 3? Alright. 4. time we have a rate function here. Instead of a quantity function, we have a rate function here with its gallons per minute versus minutes. And if you look at part B, it says, actually this R function is water being pumped into a tank. And the part B here gives us the rate at which water is being pumped into the tank. We have, instead of a table here, we have an actual equation. And so WT being measured in gallons per minute. Says use the model to find the average rate at which the water is being pumped into the tank for the first 20 minutes. So again, wouldn't that be same thing that we've been setting up for the other average value problems? Wouldn't that be the average value? Average value of any function is always, again, 1 over b minus a. And the integral times the integral from a to b of the function. And so in this case, keeping in mind that the w over wt function would give me the total gallons, because the function itself is gallons per minute versus minutes. So the area under it would give me gallons. Okay. And then if I divide it by minutes, I'd be back to gallons per minute, wouldn't it? Okay. So it would give me the average rate at which water is being pumped into the tank. Just keep in mind this W is the rate at which water is being pumped into the tank. So if we do an average value of it, we're going to get the average rate of change of the water being pumped into the tank. Okay. And again, units here again would be gallons per minute. Anytime we do an average value of the function, the units are always going to be the same as whatever the function was. What else? Number 4. And A, it says use right Riemann sum to approximate this value. So if we want right Riemann sum, we can see that we got 0 to 4, 4 to 9. Those are non-uniform subintervals. True? So that means we can't just go 2 times and a bunch of heights like we did last time. And we need to consider each rectangle individually. And if we're going right Riemann sum, that means that we don't consider the left endpoint here. So if you want to work your way backwards, if you want to, either way, we're going to have the first rectangle we have is going to have a length of 3 on the bottom. So I'm going to just go backwards just because I think it's easier. It's going to be measured at the height of the right endpoint, which is 46. So the first rectangle will be a 3 by 46. And again, I can do this without drawing it because I can visualize it in my head. If you can't do that, draw a picture. Okay? So it's up to you. I mean, I would draw a picture if I were you, if you can't visualize what values need to go where. Okay? Just draw yourself a picture of this. You know, you got the points right there. Draw a picture and then draw right rectangles for it. I'll start at the right endpoint and draw towards your left. And then the next one would be 19 and 7. So those two, the difference would be 8. And the height would be the next height, which is 42. The next one goes from 9 to 5, or 9 to 4 that is, which is 5. The height would be the 33 height. And then the last one goes from 0 to 4, so that would be 4. And the height would be the 28 height. And again, we don't use the height for the 25 because that's the left end point. Alright, and then ultimately the issue here is if we add those all up, then we get, here's where I got that number last time, this is 751 gallons. And remember, we're accumulating it's an R of t function, which is gallons per minute versus minutes, which means the integral is going to give us total gallons. Okay, so that's how many gallons. And then the other question is the approximation greater or less than the true value? We have an increasing function and we do a right Riemann sum, the rectangles are going to be above the curve. Okay, so therefore, this is going to be an overestimate. Anytime it's an increasing function, a right Riemann sum will be above the curve, rectangles we draw. For a left Riemann sum, it would be below the curve, and therefore we'd have an underestimate. What else? Number 4.
Wait, if you're trying to decide between the over and under, is it like concavity?
Not for right and left track. Not for right and left.
Is that for trapezoid?
Yes, the trapezoid would change with concavity. If it's trapezoid rule, if it's concave up, it's going to be an overestimate. Concave down, it's going to be an underestimate. And again, if you forget, just draw a picture. You know, if you were to draw, if I had something that was concave down like this, you know, some curve like this, those rectangles would be above. Whereas if I had something that was concave up, and I connected these points, it would be below, wouldn't it? So concave up the overestimate for a trapezoid. Concave down would be an underestimate for trapezoid. In terms of left and right, so if I have something increasing, if I do left Riemann sum, I'm going to be drawn below. If I have right, I'm going to be drawn above. So left and right have something to do with increasing and decreasing. Trapezoid has to do with concavity in terms of whether it's an over or an under. What else? Something else on number 4? Alright, how about number 5? We have a velocity equation here. Not equation, but table, I should say. Anything on any parts of number 5? What? See, we're given an equation here. It says car B travels along the same road, given an acceleration of 2t plus 2 feet per second squared. And it says at time 3, the velocity of car B is 11. And the question is, which car is traveling faster? Well, ultimately, if we have the acceleration equation for this car B, the question is, can we find, if you will, can we find an equation for this? We already know that at time 7, car A is going 61. So we know car A's velocity, that's in the table. So we need the velocity for car B. So how are we going to find the velocity if we know the acceleration? Just anti-differentiate. The velocity here of car B will be the antiderivative, which would be t squared plus 2t plus c. And keep in mind they gave us the initial condition here is time 3. The velocity is 11. So if we use that, we'd have 11 here. And if we put a 3 in there, we're going to get 9 plus 6 would be 15. So -4 would be our c here. So that means our velocity of car B at any time would be given by t squared plus 2t minus 4. And we need to know the velocity at 7. So if we plug in 7 to our equation, we're going to get 49 plus 14 minus 4, which ultimately would be 63 minus 4 would be 59. And we're dealing with what, feet per second? And so if this one's 59, this is car B's velocity, 59 feet per second. How does that compare with our velocity up top for car A? 61 up here, so that means that car A would be going faster at that time. Questions on any of our work there? What else? Number 5. Mike? Says use the data in the table to approximate the distance traveled by car A over 0 to 10 seconds using the trapezoidal sum with 4 subintervals. And again, with the trapezoidal sum, we're going to look and see if we have uniform subintervals, and we certainly don't because it goes from 0 to 2, 2 to 5, and so on. Right? So that means that these 4 trapezoidal approximations that we're going to create here are going to be, again, if we could, if it helps draw a picture, feel free. You got 0, 0, you got 2, 9, you got 5, 36, and we're out of space here. But bottom line here is we're going to create trapezoids with our points in question. And the fact that this one starts at 0, 0 makes the first shape actually not a trapezoid, it's actually just a triangle. And that you could still use the trapezoid formula, just one of your bases would be 0, which ultimately is just a... Okay. So ultimately here, in that first one we'd have a half times, and what would the height be? Height is always going to be the distance in the interval here, which in our case is 0 to 2, so that means our height is 2. And then our base is going to be the height on this side. And so therefore we'd have 9. So that would be the area of this triangle right here, that first triangle that gets created. The next trapezoid, x-wise, goes from 2 to 5, so that means our height would be 3. And then our 2 heights that we'll use are 9 and 36. And then the next one goes from 5 to 7, so that means we've got a height of 2. The 2 heights we'll use this time are 36 and 61. And then the last one goes from 7 to 10. So that means height would be 3. And then the 2 bases are the last 2 y values, 61 and 115. And ultimately from there it's just a calculator problem. So punch all that in and add it up, and if we do that correctly, we should get looks like 437.5. And keep in mind, if we find the that is the distance traveled here, because, and how do we know it's distance traveled instead of displacement in this problem? Because normally just a straight up integral of that, which is essentially what we've done, would be displacement, not distance traveled. What makes this not only displacement in this case, but also distance traveled?
It's always positive.
Yeah, it's always positive. It's always positive. It's not only going to give you displacement; it'll give you the distance traveled. The only time the integral won't give us total distance is when we have something that goes into the negatives, something that goes negative value. Since it doesn't go negative value, then it's just going to be a straight up integral here. What else?
Did you use like hours for that one?
Well, you could have, but it said use trapezoidal sum. So,
When do you use anyone and when do you specifically use like?
well, you use specific ones when it tells you what to use. So when you can use anything you want, I guess. If it just says approximated, I guess most of the time it's going to tell you what to do, though.
Okay.
Otherwise, then the graders will have to answer too many vague questions because everybody will do it a different way and too many varieties of answers. The graders don't want to have to look at 14 different possible answers, do they? Anything else? Number 5. All right. How about the last one here, number 6? Parts of number 6. Another velocity function, centimeters per second versus seconds. Jeff?
For number A, it says like 150 equals 20. Is that because it only like passes 20 twice?
Keeping in mind that the fact that this is a differentiable function, and keep in mind that also differentiability implies continuity, which is important here because if we're going to invoke the intermediate value theorem, which is what they're asking us for here, we need to have continuity, since this is a continuous function, okay, based on the fact that it's differentiable. If it's differentiable, it's continuous. Okay, so since we know that, it says based on the values of the table, what's the smallest number of times at which the particle's velocity could equal 20? Well, keep in mind we're at 0.37 here and we're at 2.17 here, so what had to have happened between time 0 and time 2? We had to have crossed 20. The intermediate value theorem guarantees that. And again, we're not talking about the mean value theorem. That has to do with slopes and derivatives. Okay? This has to do with y values. The intermediate value theorem guarantees that if we go from, in this case, 0.37 to 2.17, that we would have had to cross the y value of 20 at some point, at least once. Okay? So we crossed it at least once there. Did we cross it here necessarily? We might have, but we don't know for sure. Okay? It went from 17 to 5. The only thing we can guarantee between these 2 points is that it hit every y value between 17 and 5, which 20 is not one of those. Okay? So no here, no here, no here, no here, and then one more time back here. So ultimately had to cross 20 at least twice, okay, based on the intermediate value theorem's guarantee. Okay. What else on number 6?
For me, I don't get it 'cause it never crosses like the x-axis.
But again, we're talking about the acceleration, keep in mind. So isn't that the derivative of what we have here? Now we're talking about the mean value theorem. Okay, the question here is what's the smallest number of times at which the acceleration could equal 0 in this open interval? Okay, so keep in mind the acceleration would be the derivative of this function. True? And if you look at the function itself, what do we notice about the y values of the velocity here? It goes down to 1 and then back up to 38, 37 up to 38. Okay, so ultimately, again, this being a differentiable function means it's going to be a smooth curve, right? So if it goes down to 1 and then back up to 38, there needs to be a minimum there somewhere, doesn't there? Okay, so the question of what's the smallest number of times at which the particle could equal 0 in that open interval? It has to be at least once, doesn't it? I mean, it only changes direction as far as we can see, it only changes direction once. Okay. Goes down and then straight back up, if you will, right? So there has to be at least a minimum here somewhere. So that means if there is a minimum, our acceleration would equal what? 0, because the acceleration is the derivative of this curve. And the other argument you could make here is because since these are both 17 right here, what would be the slope between these 2 points right here? What would be the slope between these 2 points? So since the slope would be 0 between 2 and 10, the mean value theorem guarantees that between 2 and 10 there's 1, right? Or the mean value theorem, if we have a differentiable function, it guarantees that if we have that somewhere in the interval, the slope between the endpoints equals the derivative. Okay? The derivative is acceleration. The slope between these 2 points would be 0. So the mean value theorem guarantees somewhere between 2 and 10, okay, there's going to be a slope of 0. What else? Anything else on number 6?
Wait. Yeah, no.
Right. Just like average velocity is change in position over change in time, what would average acceleration be? Change in velocity over change in time. That's your average acceleration. So ultimately, don't I have the information there for between 8 and 10? This would be the slope. The slope of 8, 6, and 10, 17. Average acceleration is just the change in velocity over the change in time. Just like average velocity is the change in position over the change in time. So if we want the average acceleration, we can just take the 2 velocity points in question, find the slope.
Say you set up an integral thing for that. Why?
The only reason you can't set up if you want average acceleration here, if you want to treat it as an average value function, you'd need the acceleration function, wouldn't you? Do we have an acceleration function here? So you can't treat it as an average value because you could go 1 over 10 minus 8 times the integral of a of t. But what don't we have? We don't have a of t.
Don't you just need the b of t?
We want the average acceleration. The integral would be 1 over b minus a times a to b of a of t dt. Where the average value of a function is the area under its curve times the length of the interval, or times 1 over the length of the interval. So that wouldn't do us any good in this case because, like I said, we could try to write that. We could try to write that and then go 8 to 10 of a of t dt. That would give us the average value of the acceleration function. But again, what don't we have? We don't have the acceleration function.
Wait, I wonder why you can't just like do the other thing, so you have b t, and then you know what the ones are for b t.
We don't have,
Because isn't that the anti-derivative?
what are you taking the anti-derivative of? Where'd you get that?
You don't need it, because you're just getting right to b t.
You need to
Because
start
you have the
somewhere.
values in the table.
Alright, so if you did do this though, I mean, if you did the antiderivative of v of t here, okay, what are you going to wind up with? You're going to end up with v something minus v something. And you're going to put it over this. Isn't that going to be the same thing we just did? So, yeah, I guess, yeah, with that particular, I guess since you have the data in here, you could do that, I guess. Because ultimately you're going to wind up with v of 10 minus v of 8 for the integral part, aren't you?
Oh yeah, so it's the same thing.
And isn't that the y values of the v subtracted? And then what are you going to divide them by? The times divided by 2. So, it's the same answer either way. So, yeah, I guess you could think of it as an integral, as an average value, and that would work out okay in this case too.
Yeah.
So that's okay.
Outside the box.
Yeah, I guess that, as long as you have the right data in here, if they gave you 2 points that weren't actually in the data table, then you definitely couldn't do that because you wouldn't have enough information to do the v's. So. Yeah, part D says use the midpoint Riemann sum to find the values of the v of t. So if we want midpoint here from 0 to 12 with 3 subintervals, if we go from 0 to 4, 4 to 8, and 8 to 12, that would be 3 equal subintervals. True? So that means our lengths on the bottom would be 4 of each of our rectangles that we drew. Okay, the heights are going to be measured at the midpoints, and what would be the midpoint between the 0 and the 4? It would be the value at 2, which is 17, and then the value at 6 is, and the value at 10 is 17, so ultimately that would give us a total here, and keep in mind that would give us a total of what? This is going to be our v of t, which is centimeters per second versus seconds, so we get a total of something odd amount of centimeters. So we get 35 times 4 would be 170. Oh, 140. How about 140? 35 times 4, so we get 140 centimeters, or 40 centimeters. Alright, and again, using the correct units, explain the meaning of this definite integral in terms of the particle's motion. So ultimately we get 140 centimeters, and this would be the what? Be the total distance traveled. Okay. Why is it total distance? Gotta be a little bit careful with saying that though. Do we know for sure that there's no negative values in here? So do we really want to go with total distance?
No.
The only way we could go with total distance if they had told us in the reading up top if it was all positive valued or something. If they told us that v was always greater than 0. Okay. I mean, the values that we have are all positive, but does that make a guarantee that we don't have any negative values? So therefore, instead of saying total distance, though, we want to say that that is the displacement. Okay? So unless they put an absolute value around that, you don't want to ever say that's total distance unless they give you some other insight as to the fact that it's positive value. Okay? So you'd want to say that this is total displacement. And again, it might be total distance traveled, but we'd need to know a little bit more information to make that for sure. Does it say that? Oh, you're right, it does. It does say positive velocity, so since we do have that extra insight, then we can say that it is total distance in this case. I didn't see that positive velocity part. So not only is it total displacement, but it's also what? Also total distance. Yeah, so. What else?